Welcome back. Today we have text problem 28-18 for lesson 35. Alright, as always, get out a blank piece of paper or a blank printout of the problem and follow along. Now, as we get into this, we're looking at the read step here. There's lots of things to pull out of this, both said and unsaid. So first and foremost, we can see on our right a picture or a diagram of what this charged particle is doing or how it's behaving. We see that is traveling in a circular path. So if we have something traveling in uniform circular motion, hint, 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 uniform circular motion, then we're going to need to bring in Newton's second law. Now, as we bring in Newton's second law, that means we're going to have forces acting on our body. So our next question is, what is our centripetal force acting on our particle? Well, we know that it is immersed in a uniform magnetic field, and at any point on its circular path, it has a tangential velocity. Well, if we have a charged particle with a velocity immersed in a magnetic field, that should scream the Lorentz force. And one other key thing we might point out is the fact that it is in a region of uniform magnetic field. That makes the uniform circular motion possible. If the magnetic field were different on the left side than the right side, then we wouldn't have a nice, pretty circle. We would have something much more chaotic. Now, as we get into our next step, the draw step, we are given a diagram, which is helpful, but we can add to it to really pull out what's going on with this particle. So as we look at our particle, I want you to take a second, and hopefully you're not looking at the solution as we go. Draw the force, the centripetal force vector acting on our particle, the direction it's pointing, and I want you to draw the tangential velocity vector as well. And I will see you in a second. Alright, so it should look a lot like this, where our force vector that is keeping our particle in uniform circular motion is pointing towards the center of our circle, which is about right there. It is always center seeking, so whether it is on the left side of the circle or the right side of the circle, top, bottom, anywhere on the circle, it's always pointing towards the center. Likewise, the tangential velocity is always pointing tangent to our circular path. So in this case, it's pointing down and to the right. Alright, so that covers our draw step. Now we look at our givens. We're given the magnitude of our magnetic field. We're given the magnitude of the force. In this case, it's what I have labeled over here in blue. This is our centripetal force. And the charge on our particle is either positive or negative, proton or electron, 1.602 times 10 to the negative 19 coulombs. So we know the charge, the magnitude of the charge on our particle, just not the sign of our charge. And we will figure that out here shortly. Our next step is the assumption step, and it doesn't say it in there, but we assume that there's no electric field present. If you have an electric field and you have a charged particle, you inherently have a force on that particle. Well, if we have a particle in uniform circular motion, then we have to assume that the only force acting on this body is our Lorentz force and not our electrostatic force. Next up, we have our tasks step. Our first step is to calculate the speed of our charged particle, its tangential speed. Next, we need to calculate the radius of our circular path. And lastly, we need to calculate the period of this circular motion, or the time it takes to go one full complete rotation around the circular path. And it says it in there, it's not part A, B, or C, but is required to do them, is this portion right here where it says you must decide what type of particle you have. So that's kind of like a step 0. Determine whether it is electron or a proton, which I have denoted as Q greater than or less than 0. And that will denote whether we have a positive sign for a proton or a negative sign for an electron. Alright, so let's go ahead and move on to the next page. Now that we've compiled all this information and we've done all this thinking, let's put that to use in the physics step and write down the equations that you think you will need to solve this problem. So go ahead and pause the video, and I will see you in a few minutes. Alright, welcome back. So let's see what we pulled out of our kit bag. During my read step, the first thing I identified was uniform circular motion. So the centripetal acceleration, or the acceleration in the radial direction, is the tangential speed squared divided by the radius of our circular path. This is the equation that we identify with uniform circular motion. We might need that. Not for sure, but pretty good guess. Alright, next I figured that we would probably need Newton's second law, so I wrote out Newton's second law. Next we talked about how we have a uniform magnetic field, we have a charged particle with a velocity, so we have our Lorentz force. And lastly, for part C, we need to know the period of the motion. Well, I have an in-between step here. I wrote out the circumference of a circle, and I related the circumference of the circle to the period of our motion. So the time it takes to go all the way around the circle is the circular path length, which is our circumference, divided by the speed that it's going around the circle. And that gives us our period. Alright, so we have got all this information. It's looking good. I think we're ready for the solve step. So part A. Oh, let me back up. Part 0. We need to determine if this is an electron or a proton. And we can do that really, really easily. And it's called the right-hand rule. Now this shouldn't be new to you all, but we're going to use it a little differently, and you'll see how in a second. Alright, here's a picture of my right hand. I'm going to show you how to apply the right-hand rule to our Lorentz force equation. Because we have a cross product, we can apply the right-hand rule. Each of the vector quantities in our Lorentz force equation are represented by my fingers and thumb. So I'll show you which ones represent which ones. So my thumb points in the direction of our tangential velocity. My index finger points in the direction of the magnetic field. And the force vector points in the direction of my middle finger. So I want you to do the right-hand rule on the drawing that we have shown on the diagram. So put your fingers in all the right directions and let me know what direction your middle finger points. Did you notice that your middle finger is not pointing in the direction of our force vector on our diagram? That should tell you that we are working with an electron. Our proton, because it has a positive charge value, works with the right-hand rule perfectly. If you find that when using the right-hand rule that your charged particle is not behaving as it should, not following the right-hand rule, then you're working with an electron. Alright, so now that we've determined that, we now know the sign of our particle. The sign of the charge on our particle. Now on to part A. Alright, we must calculate the speed of our particle. Okay? Well, looking at our Lorentz force equation, we know the magnitude of our force and we know the magnitude of our magnetic field. We need the magnitude of our velocity, which is the speed. So rather than work with this cross product as it is, let's transform it into magnitudes and angle. So from your PRC in the bottom left-hand corner on the back, we see that we can rewrite our cross product as the magnitude of our force is equal to the charge of our particle times the magnitude of our velocity, which is the speed, times the magnitude of our magnetic field, times the sine of the angle between our vectors. If we ever want to find the angle between our vectors, we need to do a vector diagram. So let's go ahead and do that. Take a minute, draw a vector diagram of the situation that we have on the screen. And I'll see you in a minute. Alright, so here is a vector diagram. We have our force vector pointing to the right, our velocity vector pointing directly downward, and our magnetic field pointing out of the screen. Now we have three vectors in this case. The question you need to ask yourself is, which two vectors do I actually care about? What is the angle that I'm looking for between the vectors that are in the cross product? Well, our cross product is the velocity crossed with the magnetic field. So we need to identify the angle between those two vectors. So as we see from our vector diagram, that our velocity vector is pointing down in the y direction. If the y direction were positive, pointing up, and our magnetic field is pointing directly out of the screen. We can call that the z direction. So we see that based on that, the magnetic field and the velocity vector are 90 degrees apart. I can rewrite this vector diagram to better visualize the magnetic field and the velocity vectors. So let's do that. So the alternative way of writing it looks like this. I've rotated my coordinate system such that the force vector pointing to the right is now pointing out of the screen. And the magnetic field that's pointing out of the screen is now pointing to the left. It's like turning a page in a book. That's the direction of motion that I changed our coordinate system. Now that we have rewritten our coordinate system, we can see that the magnetic field and the velocity vector are 90 degrees apart. And the sine of 90 degrees is just 1. So now we can rewrite our Lorentz force like that. Now we need to find the speed, so we're going to rearrange this equation and solve for v. Now because we're asking for the particle speed, we're not going to put in the sign of our particle or the sign of the charge in our equation because we just want the speed, the magnitude of our velocity, not the velocity, magnitude, and direction. Okay, so put in our given values and we get 4.99 times 10 to the 6 meters per second. Seems pretty fast, but it's still just hovering around 1% the speed of light, so not that fast. Alright, let's move on to part B. Alright, part B asks us to calculate the radius of our circular path. Now I'm going to give you a quick hint. Remember that we are working with a particle in uniform circular motion. So I want you to first draw a free body diagram of our particle as it's going through uniform circular motion. And once we've done that, we'll come back to our Newton's second law analysis after. Alright, so how'd you do? Well, hopefully you remember that when you do a free body diagram for an object undergoing uniform circular motion, the direction that we care about most is the radial direction. So you'll notice that my coordinate system has a y direction, but it's more or less inconsequential. But more importantly, I have my radial direction. And because we have a centripetal force, which happens to be the Lorentz force, it is always pointing in the radial direction. So, now that we have a good free body diagram for our particle undergoing uniform circular motion, I want you to do a Newton's second law analysis in the radial direction for our particle. See you in a minute. Alright, so here's our Newton's second law analysis in the radial direction. We only have one force acting on our particle, and that is Lorentz force. And we have that Lorentz force equal to the mass of our particle times the acceleration in the radial direction. Now, from this, do you see an R for radius? Well, we do have our subscript R, but that's not a variable we can actually use. So at this point, we have to go back to our read step or our physics step and look at how we can relate our acceleration in the radial direction to our tangential velocity, tangential speed, and the radius of our circular path. Before we move on, my daughter would like to say hello. Say hello.
Hi, Dick.
Translation, hi, cadets. Alright, moving on. So, our acceleration in the radial direction can be rewritten as... Now, we need to know the tangential speed of our particle, which just so happens to be what we solved for in part A. Alright, now, just like we did last time, we're going to simplify this cross product in terms of magnitude and angle. Alright, now that that's simplified, can we now identify some variables that are shared on both sides? Yes, we can. Our speeds occur on both sides. One is squared on the right side and the other is just to the first power on the left side. Now I've rewritten our equation to solve for our objective variable for this part of the problem, which is the radius. Now this does mean that we're going to need to know the mass of our electron, which just so happens to be on the back of your PRC. So as we put in all of our given variables, we get the radius to be 7.09 times 10 to the negative 3 meters, or about 7 millimeters. Alright, so let's move on to part C, which asks us to calculate the period of the electron's motion along its circular path. So I want you to develop a algebraic solution to part C, but I want you to use the equation that you developed in part B and part A, as well as our physics step. So I want you to draw it down to as few variables as possible before you put in any constants, and let's see how you did. Alright, so how'd you do? Well, I'll work it through. Now we have 4 equations that we need. 2 come from our physics step, that's equations 1 and 4, and equations 2 and 3 came from parts A and B respectively. Now let's first substitute 3 into 1, and we get... Next, we need to put this equation into equation 4. So now our equation reduces to this. We have 2 pi times the mass of our electron times the speed divided by the charge of our electron times the magnitude of the magnetic field times the speed of our electron. Well, as it turns out, our speeds cancel, and it appears that we don't need equation number 2 at all. So the period of our motion reduces down to 2 pi times the mass of our electron divided by the charge times the magnitude of the magnetic field.
Daddy, I want to.
We get 8.93 times 10 to the negative 9 seconds. That's 8.93 nanoseconds. Now that's moving pretty quick. Now this is a pretty long problem and involved, but thanks for sticking around. And I just want you to remember that no matter how hard you work, there's always a dog somewhere doing absolutely nothing.